Intermolecular forces. The attractions between molecules are not nearly as strong as the intramolecular attractions that hold compounds together. Intermolecular forces. They are, however, strong enough to control physical properties such as boiling and melting points, vapor pressures, and viscosities. Intermolecular forces. These intermolecular forces as a group are referred to as van der Waals forces. Van der Waals forces, dipole-dipole interactions, hydrogen bonding. London dispersion forces, ion dipole interactions. A fourth type of force, ion dipole interactions, are an important force in solutions of ions. The strength of these forces are what make it possible for ionic substances to dissolve in polar solvents. Dipole-dipole interactions. Molecules that have permanent dipoles are attracted to each other. The positive end of one is attracted to the negative end of the other and vice versa. These forces are only important when the molecules are close to each other. Dipole-dipole interactions. The more polar the molecule, the higher is its boiling point. London dispersion forces. While the electrons in the 1s orbital of helium would repel each other, and, therefore, tend to stay far away from each other, it does happen that they occasionally wind up on the same side of the atom. London dispersion forces. At that instant, then, the helium atom is polar, with an excess of electrons on the left side and the shortage on the right side. London dispersion forces. Another helium nearby, then, would have a dipole induced in it, as the electrons on the left side of helium atom 2 repel the electrons in the cloud on helium atom 1. London dispersion forces. London dispersion forces, or dispersion forces, are attractions between an instantaneous dipole and an induced dipole. London dispersion forces. These forces are present in all molecules, whether they are polar or nonpolar. The tendency of an electron cloud to distort in this way is called polarizability. Factors affecting London forces. The shape of the molecule affects the strength of dispersion forces. Long, skinny molecules, like N-pentane, tend to have stronger dispersion forces than short, fat ones, like neopentane. This is due to the increased surface area in N-pentane. Factors affecting London forces. The strength of dispersion forces tends to increase with increased molecular weight. Larger atoms have larger electron clouds, which are easier to polarize, which have a greater effect. Dipole-dipole interactions or dispersion forces. If two molecules are of comparable size and shape, dipole-dipole interactions will likely be the dominating force. If one molecule is much larger than another, dispersion forces will likely determine its physical properties. How do we explain this? The nonpolar series, SNH4 to CH4, follow the expected trend. The polar series follows the trend from H2T through H2S, but water is quite an anomaly. Hydrogen bonding. The dipole-dipole interactions experienced when H is bonded to N, O, or F are unusually strong. We call these interactions hydrogen bonds. Hydrogen bonding. Hydrogen bonding arises in part from the high electronegativity of nitrogen, oxygen, and fluorine. Also, when hydrogen is bonded to one of those very electronegative elements, the hydrogen nucleus is exposed.